Right, welcome everybody to the May 2025 meeting of the Mornington Peninsula Astronomical Society, and quite a nice autumn evening it is, cold but clear. What is shown here are some of the things that have come in the news space and astronomy wise in the last month. So if we start at the top left-hand side, we see a rocket sitting in a shed not too much larger than this shed, and that was the one that Gilmour Space was due to launch last week. They had a couple of goes at it. First was an issue with an electrical connector, and then the second one, the nose cone unfortunately popped open while it was sitting on the launch pad before that they had filled it full of the fuel, fortunately. So with that one, they've ordered in another nose cone from their main factory, which is in the Gold Coast. So it was due to be launched from the Bowen Spaceport, which is about 1,000 kilometres north of Brisbane. So you're getting as fairly close to the equator in Australia as you possibly can, which has its advantages. Now, this one, when they finally get it going, it's been 8 years in the making, and it would be the first Australian rocket that's been built in Australia, designed in Australia, and launched in Australia to actually put a satellite up into Earth orbit. Now, we did have an earlier one in 1967 called RESAT, which was one from the Weapons Research Establishment in South Australia, part of Defence Science and Technology. That was launched from Woomera in 1967. It was a tiny bit smaller than this one, 21 metres instead of this one was going to be 25. The only difference was that it was actually launched on an American rocket, one of their Redstone rockets, which was like a tactical ballistic missile, sort of repurposed for putting a satellite up instead of a nuclear bomb, which of course is what the Redstones were originally designed for. So this one has been scrubbed twice, and it'll only be a matter of time before they put it up again. They said in their press release that they would be very happy if it only survived for 40 seconds, because even SpaceX failed, as you know, a couple of times trying to put things up into orbit. 40 seconds I don't think would even take it out over the Pacific Ocean. It would probably land down range of where they shot it on Australia. So they were hoping the longer the better. Its payload was a jar of Vegemite. So they were going, in theory, to put a jar of Vegemite into Earth orbit. In the case of SpaceX, what their first one launched was actually a large round of cheese. So they actually put into orbit a big cheese. Now, over on the far right-hand side there, more on the pursuit of fusion energy as opposed to the regular fission energy. Different approach taken by the Canadians. So far, a lot of the facilities attempting to replicate fusion on Earth have used huge superconducting magnets and extremely powerful lasers to try and compress matter enough to get its temperature up high enough that nuclear fusion would occur. In the case of the Canadians, they tried a different approach that has no lasers and no magnets at all. What they actually have is a sphere of liquid metal, and they make a very hot plasma of deuterium and tritium, which is hydrogen, which ultimately you'd be getting from seawater. And at the very high temperature, they inject it into the inside of this liquid metal, and then they have giant steam pistons all around it, which attempt to compress the metal in. And that technique has actually got the temperature over 100 million degrees Celsius during the test. They're really, really happy with that. And they say they're on target to actually achieve break-even in 2026, which you could probably read as being the end of 2026. So far everything is new and on track, and just a very different method to what some of the other engineering solutions around the world have been to try and get practical nuclear fusion that gives out more energy than what it actually takes in. Down in the bottom left-hand side, for those of you who've seen some science fiction horror movies to do with things coming from space, a microbe, a bacteria called Nyalia tiangongensis. You can probably guess where that has come from. Was discovered on surface wipes that were taken of the inside of the Chinese space station back in 2023. And they've been analysed, and they've actually found that it's a new pathogen which has actually mutated, and it's fairly resistant to radiation. So in other words, whereas a lot of microbes, when they're up in Earth orbit, they don't have very much protection out there from the UV, and indeed the vacuum of space, whereas this one is particularly hardy. And it's a sort of thing that horror movies are made of if you get something like this that turns out to be resistant. It's not the first time something like this has been discovered. A few years before this, on the International Space Station, they actually came across a drug-resistant bacteria that had mutated there as well, although that didn't quite make the media actually at the time. So they're obviously looking at this one with some interest, particularly if it's been able to adapt itself for repair of radiation damage. Then the final one in the bottom there, the gentleman there, is Ed Smiley from Apollo 13. Not the movie, but the real Apollo 13. He just died fairly recently at age 95. He was the one that managed to get them back to Earth safely. If you remember, with the crippled command module, they were actually had the problem of they couldn't scrub the carbon dioxide from the air, and all the astronauts would have died from carbon dioxide poisoning long before they got back to Earth orbit. And he was the one that came up with the duct tape and bits of cardboard and manual pages all stuck together with duct tape to give a very rudimentary CO2 scrubber, which indeed did the job of getting them back. So he's just recently passed. So tonight we'll do the welcome and new members. Now, new members tonight are Kate Cusack and family, Madvi Bettigeri, Daniel Midwood and family, and Peter McConaughey. Any of those here tonight? Oh, we've got one here. Okay. Well, welcome to the meeting. Normally I would point you to our secretary, Nerida, who's the new members officer, but she's on the way to, what's that, space conference, isn't it, up at Space Summit up in Sydney Way in a few days' time. So she's not here tonight. So feel free to come and say hello to anyone on committee who will now put their hands in the air to identify themselves. There we are. And we'll try and make you feel welcome. I'll look quickly at the events that have occurred over the past month and what's coming up in the coming months. Then Chris couldn't come tonight for monthly photo challenge, but he's given me a couple of slides to show. Then I'll throw over to Guido for Sky for the month, and then we'll look at how the James Webb Space Telescope was designed. And this speaker, Mark Clampin, is very, very senior in NASA in the USA. Their headquarters is actually in Washington, DC, so he's more in the executive level within NASA. So he was very closely associated with the building of the James Webb Space Telescope. Then we'll look at why rocket engines don't melt, because the exhaust coming out of a rocket engine is way hotter than any metal that, or alloy that we have here on Earth that we've discovered so far. And you'd have to say, well, why don't they melt away as the rocket is taking off? So it's actually quite interesting, some of the techniques that they use. So recent events. Now we had our work experience student have his first day on the day of one of our Mornington primary schools here in the auditorium, and that was on the 7th of May. We had two nights from Mornington Primary School that were on camp next door, and our work experience student there, shown fourth from the right, Alex Sim, from Year 10, was here for just over a week, a couple of hours each day, either during the daytime or in the evening, and we tried to give them a very good experience. Shown in that picture there from the night are those that were involved on that night, and there were others not shown here. So most notably, I mean, Phil's up there, and he was here most of the nights. In fact, all of the nights and days that I was. Greg Walton was here for most of the time as well, but he was probably locked in the observatory down the bottom at the time when Alex, his dad, took out his phone to take this picture. And Manfred and Ben also aren't shown in that photo. I'm not sure if you were there at the school night or not. Yes, Fred?
Got him one good looking bloke on there.
Oh, right. Okay. I should have photoshopped you out, shouldn't I? So he had a very good time, and I'm sure he'll write up something that he'll have to write up some sort of report for the school, I think, and no doubt that will find its way into the next or the edition afterwards of the newsletter Scorpius. And here's a couple of pictures of things there where people have actually sent me through from his time there. So on the top left there, he's down in the observatory doing a bit of smartphone imaging. I think Greg spent a lot of time there with him on the other instruments as well, and no doubt they'll find their way into Scorpius. Over on the right-hand side is from the last day, mostly, where we had a lot of sea stars present. And I think the best shot there, by far, I reckon, is probably Sylvie's one of the Sombrero Galaxy over on the far right-hand side there. Manfred was using the MPAS's own sea star, and with one of the galaxies there in the constellation Hydra. And Mark Stevens was learning the ropes on his new sea star with the Tarantula Nebula in the Large Magellanic Cloud and the Pinwheel Galaxy in Hydra as well. And as you see, that was a 97% full moon on those nights, and it still managed to get those images with that full moon in the sky, which is pretty astonishing. Now, coming up, we've got a few things. This Saturday, we've got not only the Working Bee and member barbecue that we normally have starting 4 p.m, but the Astrophotography group is having a meeting here at 6:30, so that will be after the barbecue part. And any member here who's interested in astrophotography who wants to sit in, just come along. There's no need to book or anything else, just roll in. 30th of May, assuming we get some bookings before then, we've got the Scout Cubs and Guides here at the Briars. We did have lined up for that a group of Joeys who I think was finding it a little bit challenging to get their people together in time for end of May, so we'll be putting those on at a different time. And the Scout Cubs and Guides are where we would usually call it off if there's no bookings about a day or two beforehand, so that's not guaranteed to go ahead. 3rd of June, we're down at Sorrento, so we're not here at the Briars, we're down at Sorrento at St Joseph's Catholic Primary School, and this is going to be a whole of school event, so it's only a relatively small school, as you see. There's 100 year preps up to year 6s on that night. So you're going to have a lot of small kids running around. Note the early start time was 6 p.m. down at Sorrento for that one. 6th of June, we've got the public night up here, and we don't have a speaker as yet, but we're fully booked out. Cosmology Discovery Group is on the 7th of June in the afternoon, and then we've got the special general meeting which has to look at these urgent constitution changes for the Australian Tax Office going through, which will be in the evening after that, so be a fairly busy Saturday there here at the Briars. 10th of June, we've got the Joeys here at the Briars. Again, an early start because of their really young age, and 30 anticipated for that one. Committee meeting at this stage is put in for 11th of June. It was originally going to be 3rd of June, but that unfortunately clashes with the Sorrento night. Indeed, we may even call it off if there's no need for the committee meeting, but that's sort of provisionally in there. And then the next meeting here is 18th of June. And at this stage, the current challenge is extended 1 month. And if you recall, the current challenge was to try and include something of the Earth as well as the sky. So in other words, you try to add something in there for context. And you see the example there of Liam's view of the full moon with some telephone towers actually in the front there to give you an idea of what's required. And notice the box on the right hand side, Chris is really after some info on what you've actually imaged and how you actually did it and what gear you used and actually where were you at the time as well. So not just send it in on its own, try and give a bit of context there. And he gives a bit of a plug for the Astrophotography group meeting this Saturday night, which will be after the barbecue, so approximately 6:30. And as you see, there'll be a general discussion, look at the new computer that we've got for the astrophotography side of things. And as you see, bring your cameras, telescopes and your own data, assuming that the weather is okay for Saturday.
All right, so here we have sky for the month for the rest of May and the first half of June. Again, this is the current image from the article that Nerida always writes for the Morning Peninsula magazine, and she was nice enough to include my image of the Statue of Liberty Nebula this month, so I was very happy about that. All right, let's have a look at the solar system first. Last month, I changed it up a bit and had the solar system viewed from the bottom. This time it's the right way around as you would expect it. So we're looking basically from above, from the North Pole down on the solar system. So all the planets are going around clockwise and also rotating clockwise, most of them. So this is what it's going to look like on the 1st of June, actually. I think, oh no, maybe this is around now at the moment. So we'll see in a minute how that's going to change. And just as a reminder, well, this is Earth here. We're rotating counterclockwise like that. And of course, that means that everything in this direction here, on this side of our planet, is kind of towards the morning. Everything this side is towards, well, I guess directly away from the sun is towards the night, right? And so everything that is close to the sun on this side is only visible in the morning sky. Everything on the other side is only visible just after sunset. So let's have a look at the outer planets as well. So we can see Saturn and Neptune are now really in the morning sky, in the early morning sky, whereas Jupiter is basically disappearing behind the sun from our point of view. Right, so that's, and Uranus is hidden behind the sun at the moment, so at conjunction with the sun. Let's take a look at the inner planets over the next month or so. So we will see that, well, Earth is running away from Mars at the moment, right? So Mars will get smaller and smaller in the sky for us, and also set a lot earlier in the sky. And Mercury is disappearing behind the sun, so it's going to be in conjunction with the sun and not visible. And Venus is going to be at its greatest elongation west, which means that it's basically the highest in the sky that it's ever going to be in its orbit. So that's a good opportunity to observe Venus, because it's going to be very bright and very high in the sky and actually visible well before sunrise. And so this was basically the month starting from now, so from today up until the 17th of June. So looking at the night sky in a bit more detail on the 1st of June now. So this is around 5 p.m. and so we'll start just before sunset, really. So sunset is around 5 p.m. now. You can see Jupiter there just disappearing in the glow of sunset there, and the Moon and Mars still up in the sky on the 1st of June, and will be visible. Yeah, sunset around 10 past 5 p.m. At the beginning of the month. As you can see here, the Moon is pretty close to the sun, so this will be only, I think, 4 days after the new moon, which is on the 27th of May. and then we'll have another full moon on the 11th of June, and then the new moon again on the 25th of June. Jupiter is now setting basically around sunset and heading towards its conjunction with the Sun later in June, on the 25th of June. And Mars is setting around 10 p.m., so we still basically have next month to observe Mars, and then it'll also set earlier and earlier and disappear from view for a while. On the 1st of June, as you can see here, it'll be very close to the crescent moon, so that should be a very nice opportunity to observe those two very close together. I can't remember exactly how close, but I think it's not just binocular, but even like telescope level close. So they, I think within maybe a couple of degrees or so, or maybe even within 1 degree. So if we now fast forward towards around 10 p.m., we can see Mars now setting, I think, around 10 p.m. there. And what we can see is that the band of the Milky Way is now really nice across the entire sky. The main stars that we can see, we still have the Southern Cross, the stars of the Southern Cross, very high in the sky, and the two pointers next to them. And then Antares, Spica, Arcturus, some of the more prominent stars for this month. We can still see Canopus, but it's actually getting pretty low in the sky now. And looking at the constellations for the month, well, it's really dominated by the Milky Way. So we have Sagittarius and Scorpius now very, very prominent around 10 p.m. And in terms of targets for telescopes for both visual and photography, I guess we have a lot of nice galaxies in Virgo. We have things like, oh, maybe I should go back. We have things like what we just saw, the galaxies in Hydra. We have the Centaurus A, Hamburger Galaxy, those sorts of targets that are very prominent for the next month or so. All right, let me see if I can continue this. Yep, so as you can see, between about 10 p.m. and then the early morning, not much is changing. It's mainly really the core of the Milky Way straight overhead. And then Saturn and Neptune now rise around 2 a.m. or a little bit before that. So Saturn is rising earlier and earlier and will actually come back into the night or evening sky later on. Venus, as I said earlier, is at its greatest elongation west on the 1st of June. So you could see that it was actually rising quite some time before sunrise. And yeah, you can see Mercury there basically just hiding behind the sun. And Uranus is also somewhere in there. It's just past its conjunction with the sun and rises around dawn at the moment. A quick look at the apparent sizes of the planets, all kind of at the same magnification. Of course, Jupiter is basically not visible because it's heading towards its conjunction. But yeah, Saturn is coming back. It's not as big at the moment, right? Because we're quite far away from it right now. And you can see Venus here basically as it will appear on the 1st of June. Because we're looking at it at its greatest elongation, it means that it'll actually appear as this crescent shape. So that's always fun to observe because only one half of it is illuminated from our point of view. Comets, same as last month or the month before. There's currently really not much going on. And meteor showers looks equally unexciting. So we're kind of at the end of the Eta Aquarids meteor shower, but that one peaked at the beginning of May. But technically, I think we're still within that part of the solar system where Halley's Comet left its debris, so we're still passing through that debris field, and there could still be some meteors from that meteor shower. And I think that's all for the month. As always, the sources were Stellarium, NASA Eyes on the Solar System, and the Astronomy 2025 Almanac. Any questions?
Saturn's rings still age on?
Saturn's rings are they're opening up again now, so they're not completely edge on. I saw some photos from maybe a week or two ago, and they're still very faint. So really most of what you see is the shadow of the rings on the planet. So you see it as a black kind of line across the planet. So I think it's probably still quite interesting. I haven't actually looked at it myself in the last couple of weeks. So, but they are opening up now again.
Did you see the article in the press last night about that meteor into a salt lake?
Ah, no, I didn't. I missed that one from last night. Okay.
Meteorite, sorry.
Meteorite into a salt lake. In Australia? In Western Australia, okay. Very cool.
A week ago it was, like, as in, it landed a week ago.
Yeah. Was that the one where they actually tracked it down and found the... Yes, I did see that. That was amazing, yeah. That's right. All right. Thanks.
So tonight's main talk goes for about an hour, and it's all about how the James Webb Space Telescope came about and designed. And they also talk about what comes next after the James Webb, because it's quite surprising that we're getting on for 3 years since it's launched, and I think originally it only had like a life of about 10 years, I think I remember, from the amount of fuel that it's got on board. So this gentleman here will be giving the talk, Dr. Mark Clampin from the Astrophysics Division. He's the director in NASA at Washington, D.C. He was previously the James Webb Space Telescope's Observatory project scientist out at the Goddard Space Flight Center. Now, as usual, this public lecture was given by at the Royal Institution in London in Albemarle Street, and is usually extremely high quality. So this talk was getting on for October last year, so it's a few months since then, but it's still nevertheless very recent. So it goes for about an hour.
Thank you. So I wanted to start by just asking, who's actually seen a launch here? Is anybody? One or two? There's a few. Great. So this is the launch of the James Webb Space Telescope. I'll just let the noise run for a minute.
And liftoff. Décollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe.
So I'll stop it there. And the point I want to make is that launches are really amazing. They're loud, they're noisy, you feel the ground moving underneath your feet. And sometimes really big launches like this one, you actually feel it in your bones. And this was a really interesting launch because very few of us could actually go to see it, where you were all stuck, basically in houses, or some of us got to go to some of the areas where we were watching the operations. And we're all wearing masks because it was Christmas morning, 2021, so right in the middle of COVID. And I was really surprised by this launch because I've been in this business 35 years. I've seen numerous launches, and I'll show you a bit in a minute. But this was the only mission where people from the street, all down the street I live on, and places nearby, came and knocked on the door on Christmas morning and congratulated us on this splendid launch, which showed on TV, I think, all over the world. And they, to a person, all said, well, we bet you're really glad that's happy and that's over, and now you can start doing science. And the key part of my talk tonight is just to show you that this was just the beginning, and normally this is the hard part. And once you've launched something, you can kind of sit back and relax once the thing starts to see the sun, and you get power on the solar cells, and then you do something we call go power positive, which means all the electronics come on and things start working. So we went power positive very quickly, but that was just the beginning. And then we had this 6-month odyssey. Some of us called it 6 months of terror, and you'll see why. And from there, we could start science operations. So that's what I'm going to talk about. So I'm going to basically just lay out, why we built Webb, what were the goals in building this very large space telescope, explain to you why it took another 6 months just to get this thing unfolded and assembled in a way that we could start doing science with it, and then talk a bit about some of the science that we're actually doing with this mission. So you already heard my CV, but I wanted to show this chart for just a minute. So I started my career, I went to University of London and then University of St Andrews in Scotland. And when I completed my PhD, I had the opportunity to go to Baltimore and work on the Hubble Space Telescope. So I ended up actually working on 4 of the servicing missions, and for one of them I was actually one of the team that built one of the instruments. And then after that, I was hired by the Goddard Space Flight Center by NASA, the real NASA, as opposed to the institutions that we fund to operate these missions. And Dr. John Mather, who subsequently won a Nobel Prize for finding the temperature of the early universe, had me become the project scientist for the observatory. So as I'm talking to you tonight, this is why I'm talking about this, because it was a really long 15-year labor of love getting this telescope from designing the first science requirements and then following that through as we worked with the engineering teams to turn science requirements into a real observatory. After we delivered the telescope, I actually moved into management and took over as Director of Science at Goddard, but I was still managing the James Webb Space Telescope project science team in that role. And now I'm the Director of Astrophysics, so I actually manage the science team that are running Webb, and you can see from this thing I call the swoosh chart, which has all of the missions that we operate or are going to operate in the Astrophysics Division at NASA. So we have an annual budget, which is on the public record of about 1.5 billion. And our job is to operate the science missions that we have flying, to develop the next generation of science missions, and then conduct research and technology programs with those missions. So it's a fairly broad portfolio, and we cover missions that study everything from gamma rays coming from merging neutron stars to studying the very early universe with the Webb telescope. So let me start with a story. So when Hubble was repaired in 1993, and they actually started getting real images, and for those of you who are too young, when we launched Hubble and took the first images, they were aberrated. It had spherical aberration. And that was a big shock to everybody, but NASA put a lot of work into figuring out how to fix that. And in 93, we launched Hubble in 90. By 93, we were able to put a servicing mission up that actually fixed the optics on the telescope by putting essentially corrective mirrors or lenses in all of the instruments. And one of the things that started taking people's attention almost immediately was when they took images of areas where there might be a star or a nebula and then background areas that were dark, they weren't seeing things that were dark. They were seeing these sort of wisps or very small galaxies. And so one of my colleagues, Dr. Bob Williams, who was the director of the Space Telescope Science Institute at that time, decided that something needed to be done here. We were obviously missing something in our understanding of the early universe, and the only way we were going to find that out was by doing a concerted program of observations. So he put together a big review team, not quite as many people as in this room, but it was pretty big, and asked them for advice and said, how should we address this program? What should we do to figure out what these objects are? Should we do a very deep observation, or is that too risky? And they all came back and said, well, it would be great if you could do that, but we think it's risky. You could get fired, because is it the best use of observing time? Because if we had just fixed Hubble and, you could work out the sort of $1 per minute for the observations, and it was pretty high. So Bob decided he'd take a risk. And against all the best advice he got, he put 300 hours of Hubble time into doing what was called the Hubble Deep Field, the first very deep observation where we picked a piece of sky that had no stars whatsoever, seemingly dark, but for a few galaxies that came up in short observations. And he did the Hubble Deep Field. And instead of finding nothing, we found this, 10,000 galaxies in this field. And as we started to study what was going on here, we realized that we were seeing back into the early stages of the universe. So Basically, what that means is, some of the galaxies in this image probably formed about 1 billion years after the Big Bang, because that's about the limit of where we can go with Hubble. So in order to understand why we know this, you have to understand the concept of redshift. So as the universe expands, light is shifted or stretched. And so the more distant objects are redder, and the wavelength at which you see specific features move into the infrared, and infrared is heat radiation. So you probably know firemen wear infrared masks these days, or goggles. So they go into a smoky room and they can find the person who's passed out from smoke on the floor. So infrared is just heat radiation. So all that light from nearby objects we see in the visible, as you go back in time, is being shifted into redder and redder wavelengths, and then into what we call infrared, which our eyes can't see, but it's heat radiation. So if you want to look back in time using this technique, you need a telescope that can see infrared or heat radiation. And unfortunately, Hubble can only see back to a certain wavelength. So it can just see into the infrared, but not very far. And by this time, in studying these deep field images, we realized that if we could go deep enough and far enough back, we could actually peer back into the time when the very first galaxies and stars formed in the universe. The problem was Hubble couldn't do that. And the other problem was the mirror just wasn't big enough. Hubble's a 2.4 meter mirror, and we realized we needed something in the 6 to 8 meter mirror size to be able to do this. So this is how Webb was born. It was basically to try to find the very first stars and galaxies that formed in the universe, and then study how they evolved as a function of time by studying galaxies at different redshifts. But we also don't fly these really big, expensive observatories just to do one thing. So we want it to be an observatory, something that the whole science community can come and use and do whatever science area or discipline they're interested in. And so we also made sure, as we started thinking about the design for Webb, that we could maybe study the formation of stars in dark clouds. And one of the problems with Webb is it's a visible telescope, so it's the same radiation you see with your eyes, and you see all these beautiful pictures that Hubble took, but a lot of them are dark clouds of dust, and you can only see the shadows. You can't see inside. At infrared wavelengths, much the same as the fireman in the smoky room, you can see inside these clouds and see how stars are being born. And a very important issue in understanding that is, how do stars form? How are they born? What chemicals or molecules go into their formation? And then how do planetary systems form around them? So you really want to be able to study these dark clouds like the ones you see here. And at the top is the visible image of Barnard 68. And at the bottom, you can see an infrared image, and all these stars appear. So we want to be able to study each of those stars individually in these big clouds. And there will be lots of different stars at different stages of their evolution. So we can really put together a picture of how this works and how planetary systems form around them. We were also lucky because just about the time we started doing the science requirements, people were starting to study planets around other stars. So one of the things that I spent a lot of time on while I was the project scientist was making sure that we will be able to study planets around other stars. And I'll explain to you later how we do that. But first, let me talk about what these science requirements then mean when you sit down to actually design a telescope. So the first thing is, if you want to study infrared radiation, you've got to be cold. So if you can only see the infrared radiation that's coming from your own telescope because it's, say, at room temperature, then you're not going to be able to see very faint heat radiation coming from the universe. So you've got to get that telescope really, really cold. And in fact, we go to 40 degrees Kelvin, so that's 40 degrees above absolute zero. And you probably know if you've ever put, hopefully you haven't, but if you put your iPhone in a fridge, you know, it stops working well before it gets to 0 degrees. Electronics and electronic systems don't like being cold. Mechanisms don't like being cold. And here we are talking about minus 230 degrees Celsius, really, really cold. And when you get to those kind of temperatures, everything you ever knew about materials changes. You have to basically go back and learn how even the most simplest material works and behaves at those temperatures. The other thing is we wanted a big telescope. So we finally realized that we could do the science we wanted to do with a 6.5 meter telescope. Unfortunately, and at the time, the Ariane was the biggest launcher available, 6.5 meter telescope did not fit in that fairing. So we realized we'd have to fold the mirror up to launch it. And that immediately means you've got to break the mirror into segments. So we came up with the design of an 18-segment mirror, and 3 segments on each side of the mirror would fold back, and we could basically fold them around the payload for launch so that we could squeeze it into the fairing. And if you look up here at the top right in the video, you can see what the package finally looked like when we got everything sorted out. The other thing, and people always ask me about, well, why can't you service this telescope? The middle panel on the right is why you can't service this telescope. When you build things to work at cryogenic or extremely cold temperatures, you have to do a lot of work covering them in what's called multi-layer insulation and really focus on making sure they can get to the right temperature. And so that really excludes the notion of putting them in a box that you can just pull in and out like we did on Hubble. You really have to gift wrap each piece of hardware individually, and you're slowly building up these instruments with all this gift wrapping on them, and then you put them in a structure like the one you see there, and there's no way you can tear that apart in space and put a new instrument in. So there was no way we were ever going to be able to service this mission from day one. The other thing that I want to mention is this had a new concept. So we wanted it to be an observatory, as I said, and that means that it has to last more than a couple of years. So NASA had flown a few infrared telescopes, and they were pretty small, and the way we got them cold was to fly them with a big dewar or drum full of liquid helium. And that liquid helium slowly boils off, and when it's done, you don't have a cryogenic telescope anymore. You have a room temperature or a warm telescope. So we didn't want to have this run for just 2 years. So we came up with a new way of thinking about how we get these things cold, and that is that you have these massive membranes, and you'll see more about these as we go through the talk, that would allow you to shield the telescope from the sun. So you fly this telescope so that the telescope and the instruments are always looking at cold space, and the sun shield basically protects them from seeing the sun so that they can actually get cold. And I'll come back to just how challenging that turned out to be as we go through the talk. But that's basically how it works. As I said, the problem is you can't fly it like this. So then you have to fold everything up. And as you start to look at what it takes to fold it up and then unpack it again once it's in space, you start to realize there are a lot of challenges that kind of creep in as you do this development work. It's kind of a reverse origami puzzle. That's how I always thought of it. So the first thing is the mirrors. So as I said, we built a mirror made of segments. Now, this had been done on the ground already at the Keck Observatory, but they didn't need to fold theirs up to take it anywhere. They took it to the mountain piece by piece. We couldn't do that, so we went with a concept where we could fold what we call 2 petals around the side. And again, we come back to that temperature. Glass really didn't work that well at those temperatures, so we realized we'd have to use a different material, and we finally settled on beryllium, which is a really nasty material. It's carcinogenic, and it's very hard to polish. So normally with glass, you polish away and you do a measurement. Have I got to the right prescription? If not, then you do another measurement, and then you start polishing again, and you just follow that cycle. Beryllium doesn't like that because as you polish it, you're putting stress in the material. Beryllium's kind of like a ceramic material. So before you can do a measurement, once you've done your polishing cycle, you have to bake it. And then it's different from what you thought you had before you baked it. So as you polish these mirrors, you're in this iterative scheme where you just keep going and going until you get to the number you want. So that sounds fairly simple. But the other problem that we faced is that we were going to operate these mirrors at 40 degrees above absolute zero, but we're polishing them at room temperature. So you have to do something called cryo-polishing. So you've got to actually start by figuring out, what do I need to polish into this mirror so that when I then cool it down to 40 degrees above absolute zero, it's got the right prescription or figure, as astronomers call it. And so you end up having to develop these very sophisticated mathematical models, which work very well until you have to do that annealing or baking stage. And that then makes things a lot harder. The two mirror images you see on the far right are what the mirror looks like at ambient temperature and what it looks like when you cool it down to 40 above absolute zero. And I'm going to just do a quick segue. So we polish into these mirrors a figure, which if you ever go to the opticians, they call a prescription. And the way we determine how well we've done is what is the average deviation from the perfect prescription. And we call that wavefront error. So to give you some idea of what we're doing here, each of these segments is about 1.5 meters. The faceplate or the surface of the mirror is about 3 millimeters thick. And we are polishing them to 20 nanometers. Now, if you haven't heard what a nanometer is, it's 10 to the minus 9 meters. And just to give you some idea of what that means, a typical virus, single virus cell, is about 30 to 50 nanometers across. So we're polishing a 1.5 meter size mirror segment, and the overall error in the polishing from the perfect prescription is about the size of a virus. So that's what we had to do. But then we're trying to make sure that that's what it looks like when it's cold. So on that figure just here, the ambient surface, that's about 100 nanometers. But then when you cool it down to 40 above absolute zero, you get your 20 nanometers, which is what we're looking for. So everything, when you go to cryo or cold, gets so much harder, and you have to start and think about how you're doing things and how you're making sure that you're not putting in errors. The other thing I wanted just to emphasize, I showed you that chart of what I've done in my career. And one of the reasons I showed you that is just to emphasize an important value that we have at NASA, which is knowledge management. And what that means is every time you do a program, you walk away when it's done and you write down all the lessons you've learned. How am I not going to mess up next time the way I did on the previous program? And the big one for us on this program was, how are we not going to have another Hubble-like error? You know, we used to joke that the ghost of Edwin Hubble was sitting on our shoulder as we did this program. So how would we avoid the errors that they made when they were polishing the Hubble mirror? And it was very simple. You do cross-checks. But they did cross-checks on Hubble, and when they got the results, they were so far off of what they expected that they were disregarded. They just said, well, we probably didn't do everything right in the test. So we did cross-checks on every single mirror, and we set the criteria for the checks before we did the measurement. And then if they didn't conform to what we expected, we went off and figured out why. We didn't just say, oh, we probably messed up the test. So every single piece of glass, or beryllium actually, on this telescope was tested and cross-checked with a separate technique. So that presented some challenges, because some of the measurement hardware, we could only find one company in the United States that would make it. So we ended up having to commission other companies to make some of the test hardware, so we'd have two different versions of the test hardware to verify that the mirrors did have the right shape. So a lot of challenges there. Now, if you've got 18 mirrors, I guarantee you, and you'll see when I show you what they look like when we got to orbit, they are not all going to be perfectly aligned when you get to orbit. Just the horror of being launched means that, these things are getting shaken, they're seeing, tens of Gs, and they move. So each of our mirrors has actuators on the back which are able to move them at nanometer steps so that we can adjust them. And those actuators give us 6 degrees of freedom. So we have piston, which is up and down, tip, tilt, and rotation. So we could adjust each of the 18 mirrors and then get them to become a perfect 6.5 meter mirror. So by the time we got to the overall mirror, the error or deviation from the prescription was around 80 nanometers. So twice the size of a virus across a 6.5 meter telescope. So really challenging numbers here and really pushing the limits of what our technology partners, Northrop Grumman, Ball Aerospace, a whole host of companies that worked with us on this program could do and even measure at the time. So even simple things like how do you measure that kind of deviation from a perfect prescription without building really sophisticated test setup. We went to industry and we told them what we wanted to do. And that primarily was that we wanted to be able to test them even in a room like this and not have to worry about putting them on special benches that were isolated from the building and isolated from people driving past the building in trucks. And they came up with a very high-speed imaging technique that allowed us to test the mirrors wherever we wanted. And that technique is now being used to do LASIK measurements. Because when you go to the optician and you put your head on the thing and they do the measurement of your eye, your head, from their perspective, is moving all over the place, and so is your eye. So being able to do these very high-speed measurements is a great way of improving the quality of the measurements of your eye they do before you then go off and get a LASIK treatment. So there's a lot of things that we took out of this in terms of technology breakthroughs. The other big problem with the mirror, again, coming back to Hubble, is you want to test the mirror as you're going to fly it. And that is extremely hard. So after much searching, we came to the conclusion that there was only one place where we could test the mirror. And that is Chamber A, which is at the Johnson Space Flight Center in Texas. And not the best place if you go there at the wrong time of year, as we found out, because we ended up doing all our testing while there was a hurricane raging outside. But Chamber A hadn't really been used since the Apollo era, and I put a picture on the right there just to, show you how big it is. I mean, that's the Apollo command module and its assembly sitting there in the door. This thing has an enormous door. And so we had to go in there and figure out, one, how we were going to renovate it, because it's a national monument. And we spent a lot of time talking to the national parks about what we could and couldn't do. But one of the other things we had to do is figure out how are we going to get that telescope to 40 above absolute zero in that chamber. So we had to build a lot of hardware inside the chamber, a big shroud that we pumped liquid nitrogen into. And then inside that, we had a second shroud that we pumped liquid helium through. And the telescope then went in the center of this assembly and basically hung from the ceiling. And one of the things we learned is that if you've got everything sitting on motors, you don't actually need to go back and perfectly align everything and get an image through the whole system. You just need to make sure that you're in what's called the capture range of all the motors. So we've also changed the paradigm for how you prepare these segmented mirror telescopes for space. You basically just make sure that every mirror is sitting right in the middle of the motor range so that you can do the adjustments you need to do to get them aligned. So that's pretty cool. So it does bring some other problems, though, when you're building a telescope this big, and people kind of forget that you've got to move it around, So for just a telescope, we had to go to Huntsville in Alabama to test the mirrors, and then we had integrated it and built it at the Goddard Space Flight Center just outside Washington. Then it went to Space Park in Redondo Beach at Northrop Grumman, and then it had to go to French Guiana for the launch. So you very rapidly find that it's really hard moving these things around. So we ended up within the United States flying it around in one of these big C5 transporters, and you can see it at the bottom. And one of the things that keeps me awake these days is it just fit in the C5. You can see that big white container, the telescope is inside that. And it's just being sort of driven into the back of the plane. And there's a picture on the left that just shows you what the inside of the plane looks like. So the next big telescope we build, if it's bigger, we've got to figure out a new way of moving it around the US in order to prepare it. The other problem with these big containers is when you want to drive them from Space Park in Redondo Beach to Long Beach to put on the boat, you've got to shut down freeways in LA, which doesn't make people very happy. So we tried to do as much of that as we could at night, but you still have to shut streets, and you need big array of police vehicles in front and behind, making sure that it's protected as it goes all the way to Long Beach. So I don't think we made too many friends in LA that evening. And then we put it on a boat provided by the European Space Agency, and it goes down from California through the canal, the Panama Canal, now into the Caribbean to go to French Guiana. And we didn't fly it down because when we went to French Guiana, we found that if we took it by plane to Kourou, there was no way we could drive it in the same way you see we're driving it around LA, because there was a lot of very small roads, a lot of bridges that wouldn't take the weight, and a lot of low electrical lines between Kourou and the launch site. So in the end, we said, no, we have to take the boat straight to the launch site, and that's what we did. So even the simple stuff like moving things around when you get to this scale get to be really, really hard. So that's another lesson. So this is the other, I think, really exciting part, and I probably spent 3 or 4 years on the requirements for this. So that's actually me standing right in the middle there as it was being assembled, so you can see how big it is. When we say tennis court size, we're not joking, it is enormous. And the material is Kapton, so it's just the same as those metallic birthday balloons that you get. Very pliable material, it's slightly thicker than the material on the balloons, but not by much. And one of the things we found almost immediately is you cannot just fold this stuff up, into piles and wrap it around the spacecraft, because as the rocket launches, it rips, the air leaving the fairing will just rip these things to shreds. So, oh my God, you have to fold it up and then somehow figure out how to pin it down for launch so it doesn't tear to pieces. And turns out you have to put covers on it as well. So we spent a lot of time figuring out how to package it for launch. And then you've got 5 layers here. So we could probably get away with 3 layers. But if you're going to be resilient to micrometeoroid impacts over the life of the mission, you really need 5 so that you maintain enough margin on your thermal performance. So 5 layers, and they all have to be separated at the right separation. And the really hard part, and you can't really see it too well in this figure, but each of those layers has to be separated by a certain distance with respect to the others. So the bottom layer is actually pretty warm because it's looking at the sun, so that cannot see the telescope. And so on and so forth as you go up the stack. So the bottom layer has to be aligned with the next layer by about 2 centimeters on each side, and then the next one has to be 2 centimeters on each side. So you can imagine trying to pull out this massive structure in space, and when you tighten everything up, you've got 2 centimeters alignment on the sides for each of the layers. So really interesting problem. And all of those pins, of course, are going to be what we call single point failures. If one of them doesn't fire and release, then we can't unfurl the sun shield, and that's the end of the mission. So really nerve-wracking. So it took about 110 of these pins to hold everything down on each side for the launch. Now, this is the traditional Wimbledon way of covering tennis court size hardware, but we took a different approach. And this will just show you what happened in that 6 months after we launched. So we start with the origami puzzle. And first thing is the solar array, which went out almost immediately as it happened. 2 hours after that, we have to put an antenna down so we can talk to the world. And then after 3 days, we start working on this sun shield. So the 2 sides are pinned down to these pallets, and they came down about 4 days after launch. Then we lift the telescope off of the spacecraft bus, which is that big square box, because it cannot be in contact with all that hot electronics. We've removed the covers, so the covers are held on with these pins. You fire the pins, and the covers basically roll themselves up. And then you start pulling it out like this. And it's very nerve-wracking watching this. On the computer, when all you can see are the tensions in the cables and people sort of going through the steps, but you can't see any of it. So we couldn't see this, and you can't put a camera anywhere because it will then become a source of heat, which will prevent you doing your science. So no cameras, and we just had to keep testing this on the ground until we understood how everything worked, and then we knew what was happening during launch. And there you see the last 2 wings of the mirror come round. So even the secondary mirror has to be folded up for launch. So everything on this telescope is deployed after the launch. And just to give you a quick idea of what that looks like. So this is a highly compressed and edited video just showing you a few of the highlights. So you can see the telescope here just being slowly lowered down. And then you can see the tensioning of those sunshield layers. And you end up with a very highly tensioned set of layers that are properly aligned with respect to each other. And that's the back of the telescope where the instruments go. So what does that look like? Well, it looks like this: 50 major deployments, 178 of those release mechanisms, 155 motors, and over 600 pulley assemblies. So that's really a lot of hardware. And that, when you added everything up, came to about 250 single-point failures. Now, normally on NASA missions, or certainly science missions, we will have maybe 5, 10 at most. So 250 is pretty scary. And those release mechanisms, I was going to bring my umbrella to demonstrate, but basically they're pins, and you have a wire wrapped around the pin and then a little fuse at the bottom. And when you fire it, the fuse melts and the wire unwraps and releases a pin. So 178 of those. And 100 were holding the sun shield down. The rest were holding the telescope for the launch phase where it's getting shaken really badly. And that's because this is what some of my engineering colleagues call a floppy structure. Now, it's not, but for an engineer who sort of likes working with really stiff structures, this telescope is floppy, so everything had to be pinned and locked down for launch, so when we shook it, it didn't all come apart. And we weren't done there, so once we had finished all those deployments, we still had to lift all 18 of the mirrors another 3 centimeters off of their sort of launch location. So we had to sort of piston them all up by about 3 centimeters, and then we started the alignment. And this is what it looks like once you've got all the mirrors aligned. We were lucky that we didn't have to go hunt for any of the images, but this is how we aligned the telescope. So you start with 18 of these images, and then you start stacking them one by one, and each of these requires a separate observation, a number of calculations, and finally we get to merge them all into a single spot, and then we do a final calculation based on the spot. And for me, one of the great ironies is that the technology that we use to do this is a technology we developed, or I would say matured, after trying to figure out what was the required prescription to fix the Hubble Space Telescope. So it's a technique called phase retrieval, where you measure out-of-focus images on both sides of the focal point and use those to calculate what you need to do with the mirrors to get everything aligned up. And when you get it right, you get to a spot. And this is what it looked like. So this was a really interesting exercise for our press people, because when we planned this program, we were going to do a press release on a star. We've phased the telescope's seeing a single star, everything works, good to go. And this is the image they took. This was a few seconds, and you can see all these galaxies in the background. And so the press people are saying, well, what do we say about those? So we had to basically rewrite the whole script for this first press release that said we've got the telescope aligned, and point to the fact that clearly we were doing much better than we thought we were in terms of the image quality and the sensitivity of the telescope. And in fact, it turns out, as you can see there, the telescope's image quality was 2 times better than we expected based on the modeling. The image jitter, which contributes to that, which is how much shake the image has because the spacecraft has a lot of moving parts in it, gyros, things like that, was 7 times better than we expected. 7 times better than Hubble, in fact. And the sensitivity turned out to be 30 times better than the requirement. So in a few second image where we expected just to see a star, boom, all these galaxies appear, and everyone's like, wow, what's going on here? And it's hard to appreciate what this means, especially when you think about what we had before in infrared astronomy. But this next image really shows that. So the image that's being covered over was taken with the Spitzer Space Telescope, which has a 0.5 meter mirror, which is about the size of the secondary mirror on Webb. And you can see the same field being uncovered from Webb, and the difference is just mind-blowing. I mean, there's no other way of putting it. So once we started getting to the point in the commissioning where people were seeing real science, you know, they were jumping up and down in the corridors, everybody was giddy, and you know, you couldn't find somebody who wasn't smiling in the building. It was just amazing. So you see what that mirror... So this is just a sea change, and this is, you know, one of the reasons we build these telescopes, to really open up new discovery space. So it went on and on. So the next thing, I'm not quite sure what that is, but sorry, there's a little blue thing here that wasn't there when I made the slide. So the very first science images we take with new telescopes, we call the early release observations, and we did 4 with Webb. And we'd done pretty much 4 with all the Hubble instruments before that, and other missions that we launched. On this telescope, the first image was so amazing that the White House wanted to do the release. So we actually did the press release from the White House, and you can see President Biden standing there with, you know, the big backdrop of the James Webb Space Telescope, and we presented this image, which even today just amazes me. And what you're seeing here is something that amazingly, Einstein predicted back in, I think it was 1918, and speculated that nobody would ever actually be able to confirm his paper. And basically, the idea is that, you know, when you have very large mass, it can bend light. And so what you're seeing here is a supercluster of galaxies, and those are the white galaxies you see in this image here. And the mass of that supercluster is such that it is magnifying and bending light from galaxies that are much more distant than the supercluster. And it's kind of illustrated here in this schematic. So you see this field, it has lots of whitish galaxies, which are the nearby galaxies in this supercluster. And behind them, or superposed on the field, you see all these red wisps. And these are the highly distorted images of galaxies that are way, way behind the cluster. So, you know, we're also getting a free bump in sensitivity from nature here as well. And the thing that really I found just almost shocking is that this image from day one, normally we do what we call a few press releases, you know, we publish the pictures, everyone says, yep, it works, and then we move on and start doing science. People were doing science with this image hours after it was taken, and it is still producing new papers in the literature. And I'll show you one example in a minute. But we also got a lot of attention. So the first light images showed in Piccadilly Circus. You can see there on the left. They illuminated the Empire State Building with gold light. Coldplay showed the images at their concert that week. And you can see Times Square also showed the images. And a couple of weeks later, Jimmy Buffett showed the images at one of his concerts as well. So we got a lot of airplay for these very first images. And I said I'd show you some of the science. So that very first image, you can see this feature here magnified, and on the right there's the Hubble view of it, and on the left is Webb. And astronomers immediately dubbed this thing the sparkler. And it's just amazing, because what you're seeing here, all those little dots, it's a very distorted image of a background galaxy, and it's surrounded by globular clusters, very large, dense clusters of stars. And you can actually see the globular clusters in this galaxy. And we think these globular clusters probably formed about 350 to 400 million years after the Big Bang. So even with this very first image that we did for the press release, we're already starting to get back to that very first epoch when stars and galaxies were born. So that was really, really amazing. And right now, this is the record holder. This is the most distant object we found with Webb. It has the usual sort of telephone number nomenclature. We're not very inspirational when it comes to the names of these objects. But it demonstrates that we really are pushing back to just that time when the very first stars and galaxies formed. And what you see on the right is a spectrum. This is what you get when you pass the light coming from this object through a prism or reflect it off a grism to disperse the light into its, the colors that make up the spectrum. And that allows us to confirm that this really is an object that old. So it has a redshift of 14.3. So that's pretty amazing too. The other things I talked about, I'm going to briefly mention the formation of stars. So one of the other early release objects was this image at the top called the Cosmic Cliffs. And it seems to be very popular on T-shirts. I've seen at least two people today wearing Cosmic Cliff T-shirts. And you can actually see in this image, see inside the cloud and start to study the formation of stars, through all the different processes. And I put a few examples at the bottom of other observations. The ones at the bottom are not from the cliffs, but the first two, the Herbig-Haro and the protostar, are both star systems that are about few tens of thousands of years old. And then on the right, this is Fomalhaut. It's the second brightest star in the southern sky. And you can see this big disk of dust that is orbiting around this star. And this is debris left over after planets have started to form. And the new result from... there was a mention of this at the beginning. I was on the team that discovered this debris disk. And the new JWST image shows that there's actually an inner gap in this system that we didn't know about. And then there's another disk of warmer gas closer to the star. So we're really starting to understand how stars form and how those planetary systems around them form. My colleagues in the solar system scientific discipline would not forgive me if I didn't show at least one result from our own solar system. And I think this one is timely. We just launched a mission to go to the moon Europa. This is Saturn's moon Enceladus. And we knew from a previous NASA probe called Cassini that there were these plumes of liquid coming off of this moon. And you can see in the top left, that inset gray image, there's, I think, 3 or 4 little fingers or plumes. That's actually liquid coming off of this moon. And what we think is that it's actually got a big sea that's covered by ice. So the outer shell is ice, and there are cracks, and the liquid underneath is spraying out. So we knew from Cassini that there were these things people call plumes. And then we observe it with Webb, and we find these are not plumes, they're torrents, just masses of water coming out. And they're basically seeding the E-ring of Saturn's ring. So we were able to do a number of measurements showing that this water is coming off of this moon and then going into orbit around Saturn as a part of this ring. So this is really interesting because one of the things that we'll be doing in the future, either at NASA or the European Space Agency, is going to this moon and trying to sample this water and see if we can find evidence of molecules that might indicate, the presence of life in this moon. And then we come to exoplanets. So exoplanets are the really big thing in astronomy right now, studying planets around other stars. And there are a lot of them out there. We now know there's about 5,000 confirmed planets around other stars, and around 4,000 of those are in systems, which means there's more than one. And we study them with James Webb using this technique called transits. And I'm going to talk a bit more about this in a minute. But the basic idea is that this is a mini eclipse. So as the planet crosses the face of the star, if you're correctly aligned with respect to the orbital plane of the planets, you get a little dip in the light. So you can tell there's a planet there just from the dip. So a Jupiter-sized planet gives you a 1% dip in the light. An Earth-sized planet gives you 0.01%, really small and hard to measure component. But the really amazing thing about this technique is that if you then put that light through a prism, you can actually back out composition of the atmosphere of the planet. And this is one of those subjects where you do exactly what your math teacher told you not to do, which is to subtract two very large numbers. So we've actually refined this technique over the last few years in NASA and also in the ground-based community. And we're able to make these measurements. And Webb is ideal because you need lots and lots of light. So this is one of the very first exoplanet measurements. It's a star called WASP 39, and 39b is the planet. And you can see this spectrum. So the bottom axis is wavelength, and then the side axis is the signal level. And what you're seeing here is all the different elements in the atmosphere of this big, puffy, Jupiter-like planet. And one of the really interesting things is that JWST is so sensitive. Over here, you can see sulfur dioxide, which is produced by photochemistry, which is when the atmosphere of the star is interacting with the atmosphere of the planet. And this is something we often associate with the possibility of future habitability. On this planet, it doesn't, because it's big, massive, Jovian-sized planet. And we're also able to do small rocky planets. Those are a lot harder, but one of the things we can do is actually look at the thermal emission and figure out whether this is just a rock with no atmosphere, like Mercury, that's radiating heat, or whether this small rocky planet has an atmosphere. So JWST is starting to study a lot of planets. Now, most of the planets it's looking at are in the top box, what we call red dwarfs or late M spectral type stars. And they're relatively small, so a lot of red dwarfs are about the size of Jupiter. So you see a bigger signal when the planet goes across. JWST cannot study stars like our own sun, bigger, hotter stars. So if we're going to study those and look for evidence of life with those, we need to do something different, and that's direct imaging. So in the last few minutes, I'm just going to talk about what we do next, how we take the lessons from this mission and apply them to what we're going to do next. And I don't get to decide what missions we're doing as the director of astrophysics. I have a National Academies decadal survey that's done once every decade, and the whole science community comes together and decides what are the priorities for this decade. and they write something called a decadal survey, and that is used by Congress as they think about how to fund all the different science disciplines at NASA. So Earth science, heliophysics, planetary, and astro all get our own decadal surveys, and it's very hard to get something funded if it's a big flagship like Webb, if it's not number one in that decadal. So it's been a very successful process because it means you have the whole community behind you, and Congress know where to go to look to see what the priorities are. So the 72 decadal gave us Hubble, the 2000 decadal gave us Webb. We're just finishing up the Roman Space Telescope, which was the 2010 decadal. And my job is to implement the 2020 decadal. And that is a number of things, but the big flagship mission is to build a telescope that will search for life. So I'll just let this little video run for a minute. One of my colleagues put this together as the trail of the next mission. And it's kind of slow. Here we go. So this is what we're looking for, small rocky planets that are habitable and might potentially have life. So one of the good things about being director is you get to pick the working names for these new missions until they give it a formal name. And this one, as you will see in a second, we are calling the Habitable Worlds Observatory. So I think that's a great name because I don't need to explain to you what it's going to do. You can figure that out from the name. And that's really important, believe it or not. So what are we actually going to do? So back in 1935, a French astronomer called Bernard Liot wanted to study solar eclipses, but he didn't kind of want to wait for them to happen. So he came up with an instrument called a coronagraph, which basically did what a solar eclipse does, except he had an instrument with a small dot, and he blocked out the sun using that small dot. And then he could study all the structure around the sun. And this was a photograph taken from the last solar eclipse, and you can see these solar prominences and flares there. So this has become a technique that we use for doing astrophysics now. And what we want to do is take, instead of using the transit technique, is to use direct imaging. And that means we can study all types of stars and look for small rocky planets with atmospheres that are in an area where there might be the possibility of life. It's a very challenging problem because if you're going to look for a Jupiter, you need a contrast level of 1 billion. And if you're looking for small rocky planets like Earth, you need contrast level of 10 billion. And you can put your thumb around one of the lights here, look through it with one eye. That's basically how this technique works. But we're not just trying to block out a light so we can see the clock or whether they clean the ceiling. We're trying to find small rocky planets. And it's very challenging because they're very close to their parent stars, and their parent stars are much, much brighter. So this is the challenge. And what it means is that we have to go back and look at what we did on Webb and figure out how do we go from the Webb telescope to a telescope that can see small rocky planets. And it turns out that you have to be 1,000 times better in the prescription of your mirror than Webb. And it has to stay that way. So one of the things we did with Webb is we realized we didn't need to keep that figure by continuously adjusting it. In fact, we can't do that. But we would come back every 2 weeks and just tweak them, do a measurement, tweak the mirrors to keep it perfect. Turns out that Webb is so stable in space that we don't need to do that more than once every 2 or 3 months, which is pretty amazing. But with this telescope, we need to do it continuously, which is why it says active control. So we have to actively control the mirrors. So we're continually making those adjustments that on Webb we do once every 2 or 3 months. And we're trying to go a factor of 1,000 better than Webb. So I've got there the stability has to be in the picometer level. What does that mean? Well, it means that we're trying to get down to about the size of hydrogen atoms in terms of the overall error in aligning the telescope. And we're trying to do that continuously all the time. So this is the challenge for the Habitable Worlds Observatory, building what we call an active telescope that will be able to do these corrections continuously so that we can maintain the quality of the mirror and then use the coronagraph to image the small rocky planets. And we'll survey the nearest several hundred stars to our own solar system looking for planets like our own. What we do when we find them, well, we'll look for something called biosignatures. So a very famous US astronomer, Carl Sagan, and I'm actually really proud to be here tonight because I remember when I was a kid watching him talk right here about Mars on the television. So it's kind of cool. But Sagan figured out that he needed something to do while his missions were going to Cassini. So you saw a result from the Cassini mission and to Mars. And he had the idea, well, if I turn my mission back and look at Earth while it's on its way to Mars or to Jupiter, can I tell if there's life on Earth? And he basically made these observations and he found some of these biosignatures and concluded, yes, you could infer the presence of life by looking back at the Earth and taking spectra. So the kind of things we'd be looking for once we found these candidate small rocky planets with potential habitability would be oxygen, methane, carbon dioxide, water, what chemists call disequilibrium, and also potentially Rayleigh scattering as well. But we have to be smarter than that because, as you probably realize, different ages of the Earth, the atmosphere has looked very different. So we have to build a telescope that can not only pick and find biosignatures that look like our Earth today, but also like our Earth when life was just starting. And, you can see the simulated spectra for 3 different ages of the Earth. So we're still doing a lot of research to figure out what exactly we need to do with this telescope. And we're just getting started now, but this is the overall goal. And I'm going to finish up by just quoting from the National Academies who came up with the recommendation to go build this telescope. And it says, if planets like Earth are rare, our own world becomes even more precious. And I'll let you read the rest of it. But the one I like is Carl Sagan, who said, the universe is a pretty big place. If it's just us, that seems like an awful waste of space. So I'll finish there, but one thing I hope you sort of take away from this is that everything we do on these big missions is inspirational. And I was talking to a gentleman on the way in who was telling me, he remembered the Apollo program and watching that as a kid, and so do I. And I have people working for me now who had that same experience with the very first Hubble images, and I'm sure in 5 or 10 years there'll be people working in astrophysics who remember the very first Webb images. So what we do in NASA science, and not just astrophysics, but all the science we do, is really inspirational. Obviously, we make a lot of discoveries. Hubble completely rewrote the textbooks in astrophysics. It won 2 Nobel Prizes, and I'm sure Webb would be just as successful as we go forward. But there are other things. People often say, well, why spend all this money? So the other thing that these big programs do is they really infuse, certainly in the United States, technology into industry. So we have queues of the biggest industries, the big aerospace companies wanting to work with us because what we do really challenges them to go to a new level of, technical capability, and that then, of course, flows out into all the other things they do. So, these pushing the envelope on technology really infuses, the nation's technical capabilities. And then finally, and I mentioned this a bit already, it really engages the next generation in STEM. So astronomy is one of the most accessible sciences, and we really think that we do a great job, certainly in the US with the programs that I manage, bring in, kids from very diverse backgrounds into science or engineering or even program management, to work on these programs. People want to come and work on these programs because they're so much fun, they're exciting, they're obviously very stressful sometimes, but that's part of the fun when you finally get to see those first images. So I will finish there and take questions.
And all those hundreds of points of single failure that could have ended the mission very, very swiftly. Very impressive. Okay, well, we'll move into the next one, which is why don't rocket engines melt. This goes for about 10-12 minutes, and given by Tim Dodd from the excellent YouTube channel called Everyday Astronaut. He's a science communicator, and then we'll actually close with a flight through the cosmic cliffs, one of James Webb's first images.
Hi, it's me, Tim Dodd, the Everyday Astronaut. This is SpaceX's Raptor engine that powers their Starship and Super Heavy booster. When this thing is running, there is unbelievably hot combustion continually burning at the heart of this beast. In fact, the gases inside the combustion chamber can reach about 3,500 Kelvin, about half as hot as the surface of the sun, which is above the melting point of pretty much any material out there. But this heat is kind of what makes a rocket engine function. I mean, after all, their only real purpose is to convert the chemical energy inside the propellant into pressure, and often therefore heat, so that they can produce thrust. And that brings up an obvious question. How in the heck do engines survive this heat? How did rocket scientists figure out how to keep an engine running continuously while harboring combustion inside that's hot enough to not just melt the metal walls containing it, but actually vaporize the metal, or more pedantically, sublimate the metal from solid to a gas in an instant? But we'll just say melt for simplicity in this video. So today, we're going to talk about the tricks engineers employ to keep rocket engines from melting. This is a combustion chamber. At the top of it is the injector face. This is where the fuel and oxidizer get pumped into the chamber at very high pressures. The fuel and the oxidizer will mix somewhere downstream of the injector face inside of the combustion chamber, and they'll ignite and then combust. Assuming there's adequate and continuous flow, the propellants will burn. But with ridiculously hot gases squeezed together in between the metal chamber walls, we certainly don't want the metal to melt. So perhaps the easiest thing we could do is just make the metal walls so thick, even the scorching hot gases can't heat up all the metal enough to actually melt it. The walls act as what's known as a heat sink, or a giant thermal conductor that can handle a high heat load for a period of time before it warms up all of the metal to its melting point. The use of exotic materials might be a fitting choice here, something that can handle extreme heat and still be strong, such as Inconel or other alloys, but of course, price or weight or other factors certainly come into play. Obviously, first off, if you're using thick metal walls as a heat sink, they're going to be quite heavy. And in a world where rocket engineers would eat a hat for even a 5% weight reduction, making your engine's walls so incredibly thick they don't melt is not only far from optimal, it's downright primitive. The other problem is you can realistically only run an engine for so long before you eventually heat it all up to its melting point, so it has inherent limitations and viability. This option isn't a very good choice for main propulsion engines, where they might need to run for several minutes continuously. But this option is actually valid for smaller engines, such as reaction control thrusters. Reaction control thrusters are often pulsed and run in shorter duration burns. This allows them an opportunity to cool down between pulses. This keeps them simple and reliable, but with limitations on continuous runtime to keep them from melting. But what if you could just lower the temperature of the combustion? A less hot gas might make it so you could use thinner walls, and might make long duration burns more survivable. well, that actually is an option. The next relatively simple thing you can do to keep your engine intact is to simply run the engine with more fuel or more oxidizer, otherwise known as fuel-rich or oxidizer-rich, which can lower the temperature of the exhaust. This ratio is the fuel to oxidizer mass ratio. Now, if you wanted to burn 100% of your propellant and have absolutely as much of it react with each other as possible, you'd need to burn it at what's known as its stoichiometric ratio. This is where there's the exact amount of fuel and oxidizer to perfectly react as completely as possible with each other, which leaves no propellant left unburnt. But burning at your stoichiometric ratio also means you're releasing as much heat from the chemical bonds as possible too. While that might actually be ideal in some situations, that is not ideal in a rocket engine for a few reasons. The more heat your engine is producing, the more you need to cool your engine via other methods, so it doesn't melt, and you're going to need to employ more of the tactics that we're going to be discussing in this video. So rocket engines need to run their fuel to oxidizer ratios a bit off from stoichiometric. Main combustion chambers tend to run fuel-rich because this usually results in lower thermal loads and higher efficiency. Not to mention, scorching hot gaseous oxygen is typically avoided as much as possible, since it sure loves to turn metal into soup, and the rocket engine will end up running engine-rich, and that's definitely not good. But beyond just the main combustion chamber's fuel to oxidizer ratio, you can also run your preburner or your gas generator very fuel-rich or oxidizer-rich in order to keep it cool too. In fact, you can burn it at a different, more conservative, cooler temperature than you would your main combustion chamber. And quick side note, if you don't know what a preburner is or a gas generator, don't worry, I've got you covered. Check out my Soviet rocket engine video. In the beginning in the glossary, I go over a lot of terms that will be really helpful for this video and frankly, all videos about rocket engines. Okay, back to keeping your preburner or gas generator cool with your fuel to oxidizer ratio. This is extremely important because it's hard to cool a spinning turbine. You're really stuck with a set amount of heat that it can actually take based on the materials. And you just kind of simply have to change your fuel to oxidizer ratio until the heat load is bearable. And unlike the fuel-rich main combustion chambers, turbines can be designed to run fuel-rich or oxidizer-rich. For example, the Space Shuttle's RS-25 main engines ran fuel-rich through their preburner, while the Soviet-designed NK-33 ran oxidizer-rich propellant through their closed-cycle preburners. But all of this is rocket science we're talking about, and performance and optimization is everything. So we don't want a big, heavy engine or one that's sandbagging its performance to run cooler. But we also don't want our engine to melt. Or do we? Welcome to perhaps one of the most simple and effective ways to cool an engine. And that is, well, to allow it to melt, but just a little bit. This is called ablative cooling. Ablative cooling is where you use a material that will vaporize and gets thrown into the wake, which takes the heat along with it. It's most commonly made out of carbon composites, which have a very high melting point. This is also the same principle many spacecraft use on their heat shields. When a spacecraft is coming back into the atmosphere for re-entry, it gets crazy hot. And the heat shield just accepts that heat. It takes it right in the face. And then when the surface gets too hot, it basically melts a layer away, taking the heat with it. This prevents heat from penetrating deeper into the vehicle. And this is the same idea you can use to cool a rocket engine. Inside the metal walls of the combustion chamber and the nozzle will be a layer of carbon composites. As the propellant burns inside the engine, the carbon liner will slowly get chewed away. Now, if you're anything like me, you might think this sounds like kind of a terrible idea. But it's actually an incredibly efficient and reliable method of cooling since it's self-regulating, has no moving parts, and is incredibly effective. But it does have its limitations. Obviously, if you're looking to reuse your engine, you should probably look elsewhere. In fact, some engines may not be able to go through their full testing before use because it will wear down the ablative chamber walls. And because the chamber and throat walls get thinner, their performance can actually decrease throughout the burn, as your throat's area will increase a lot compared to the nozzle exit, which will decrease the overall expansion ratio of the engine, which is the opposite of what you want as you ascend into thinner parts of the atmosphere. And it's also quite heavy. The ablative material is just extra stuff that weighs a decent amount. Perhaps one of the most famous examples of this is the Apollo Lunar Ascent Engine, which could not be test fired as a complete unit before being lit on the surface of the moon to get astronauts home. Yes, that's a terrifying thought. Some other examples of ablatively cooled engines are SpaceX's first Merlin engine, the Merlin 1A, which flew on the first 2 Falcon 1 flights, and United Launch Alliance's Delta IV engine, the RS-68A. On the RS-68A, you can easily tell this engine is ablative because the engine runs on hydrolox, which usually has a nearly completely transparent exhaust of just water vapor like we saw on the space shuttle. But the RS-68A's exhaust is bright orange because the carbon that is ablated and ejected from the engine continues to react with the oxygen in the atmosphere, which makes it burn bright orange. Sometimes reaction control thrusters use ablative chambers too, since they are often used in short durations and have a set amount of propellant they can use before they run out, so engineers can design the wall thickness to match the maximum use case. Okay, but what if ablative cooling is just not cool enough for you? Well, then we've got a few more options to check out. Perhaps the most common way to keep a liquid-fueled rocket engine from melting is by using regenerative cooling. This is where they flow some or all of the propellant through the walls of the combustion chamber and the nozzle before it goes through the injectors and into the chamber. Yeah, that's right. Even though the walls and the nozzles of rocket engines look super thin, there's often a very small channel where fuel can run up and down the walls in order to keep them cool. This was a major breakthrough that allowed rocket engines to run more or less indefinitely. Early versions of regeneratively cooled engines would have the main chamber and then basically a liner on the outside of it to run the coolant or fuel through. Later, it became common to actually just use pipes to form the walls of the combustion chamber. In fact, the RL-10 engine still uses brazed tube construction today, although they are working on modernizing that process. A more modern practice is to mill a cooling channel in the walls of the combustion chamber and the nozzle, and then use a copper or a nickel alloy to close it off, and then that will be the inner wall of the chamber. Copper and nickel alloys are used because of their ability to transfer heat from the walls into the coolant, thanks to their high thermal conductivity. Now you might be asking, doesn't that boil the fuel before it reaches the chamber? Yeah, it sure can. And this process of boiling the fuel can actually be used to spin the turbines to run the pumps of the engines. This is what the expander cycle is. It harnesses the energy of the thermal expansion of the fuel going from liquid to gas. It is extremely efficient, but it is limited by the amount of available heat. We'll talk more about the expander cycle in an upcoming video where we go over pretty much all of the cycle types and talk about their pros and cons. Most engines use the fuel as coolant, but oxidizer could be used as well. But a fun little thing to note is when cryogenic propellants are used, the outside walls of the rocket nozzles can be unbelievably cold, while the inside of the walls are scorching hot. Talk about a temperature gradient. Check out this video of an RS-25 running. If you went up and touched the outside of it, your hand would freeze solid. Touch the inside and it'd burn off instantly. It's honestly crazy to me that these two extremes can exist in such close proximity. One of the challenges with regenerative cooling is that the pressure inside the walls needs to actually be higher than the pressure of the combustion inside the chamber. That's right. The tiny little channels flowing cryogenic fluids inside the thin little walls of a rocket nozzle are actually under higher pressure than the main combustion chamber itself. This is because of the fact that the walls are essentially just tubes that feed the injectors, and pressure always flows from high to low. So the injectors always have to have higher pressure than the combustion chamber. But it's just crazy to me that those tiny little passages inside the walls need to handle that really high pressure too. Seems like with such thin walls, it'd be so easy to spring a leak. Well, if a leak does spring, there's some good news. Let's pretend a leak springs on the inner wall of a regenerative cooled chamber. Because the pressure inside the walls are higher than the pressure inside the chamber, all that will happen is fuel will leak in a little and actually provide some additional cooling. Firefly CEO Tom Marcusic explained this to me when I interviewed him at their factory outside of Austin, Texas.
Engines are amazing, and haven't seen this here as much, but I've seen places where the engine will actually erode itself down to the point where it starts leaking, and then it's happy, and it doesn't go any further. It just like self-regulates.
Yeah, interesting. Yeah. But wait, if fuel leaks into the chamber, how would that not just make it explode more and make an even bigger problem? How on earth can that help cool an engine? Well, that brings us to our next method of cooling, film cooling.
Liftoff. We have liftoff.
Another common method of cooling is film cooling. This is where you inject a fluid between the combustion chamber and nozzle surface and the hot combustion gases. Because don't forget, fluids are either gas or liquid. So this can be done in either form with liquid or gaseous propellants. The basic mechanism at play is creating a boundary between the wall and the hot combustion gas that creates a thermal insulation with a cooler fluid in between them. So how exactly do they do this? Well, let's start off with liquid film cooling. One easy way to do liquid film cooling is to literally just have a higher concentration of fuel or oxidizer injectors on the outer perimeter of the injector face. Engineers will almost always use fuel since the main combustion chamber usually runs fuel rich. So there'll be a whole ring of extra fuel flowing around the outer perimeter that won't have the right amount of oxidizer to react with. This will produce a ring of even more fuel-rich combustion, which prevents heat from transferring from the main combustion gases and the walls. But not only that, most of the fuel closer to the walls won't react at all because it won't have any oxidizer to react with. So it actually just travels down along the walls of the combustion chamber in a film, trapped between the combusted gases and the metal walls. And if it is a liquid, it will likely phase change from a liquid to a gas, and then that'll create a vapor boundary layer, as well as absorb some heat energy in the process of phase changing. It's common to actually drill holes in the walls, assuming they're regeneratively cooled, to intentionally leak in some of the fuel, especially in particular hotspots like the throat of the engine. Another weird benefit of using fuel to cool is that you can create a carbon layer in the form of coking along the walls when using a carbon-based fuel like RP1. When you have a fuel-rich combustion, there's a lot of carbon that will be unburnt and can create soot. Just look at the exhaust of the gas generator for the Merlin engine. SpaceX runs the combustion inside the gas generator extremely fuel-rich in order to reduce its temperature so the turbine doesn't melt, like we mentioned before. As a byproduct, you see the exhaust coming out is very, very dark and sooty. This is the same type of soot that can actually stick to the walls of the chamber and often has a bad side effect, which is having that soot attached to the injectors and potentially the cooling holes or slots themselves, which can clog them up. But the soot that sticks to the walls is another thermal barrier that can help. Again, let's hear Tom Markusik explaining that. We also saw great evidence of the soot when we were up close and personal with their Reaver engines, as evidenced by the soot on Tom's face.
Also, with LOX-RP propellants, some of the products that condense on the surface of the chamber are beneficial for inhibiting heat transfer to the wall.
Right.
So once you get up above about 1200 psi, that sort of soot carbon layer starts to come off. So it kind of runs away. Your cooling problems get worse very kind of precipitously as you go over that mark. It's not just 100 psi is a little bit different because your soot goes away and now you've got much more heat transfer to the wall. So there are other factors that play into what's going on in there.
So the coking on the combustion chamber can almost aid as like an insulating barrier?
Oh, it absolutely does. It's a
really?
It's really effective thermal barrier coating for free. Really? So all that soot you saw in my face and in that chamber, that's great for thermal barrier coating.
By the way, if you haven't seen this interview with Tom, I highly recommend it. Tom is literally a rocket doctor, after all, having a PhD in mechanical and aerospace engineering. So it's packed full of great knowledge. But back to the Merlin engine with that really dark, fuel-rich exhaust from the gas generator. There's another thing we can do with that exhaust. We can use the gas itself to film cool some of the nozzle. But there are a few caveats. You obviously notice that on the sea level Merlins, they are just dumping that exhaust overboard. So it doesn't seem like they're cooling with that exhaust gas at all. But if we pop over to the vacuum optimized Merlin, we can see they do something different with their gas generator exhaust. It isn't just simply dumped overboard. Instead, that turbine exhaust gas is pumped into the nozzle extension that makes the engine optimized for use in a vacuum. In order to understand why this makes sense, we do need to remember something about a nozzle. As it expands after the throat, the exhaust gets cooler and lower pressure the further down the nozzle you go. So keep this in mind when we think about where we can pump in that turbine exhaust gas. It has to be far enough down a nozzle where it's both higher pressure than the main combustion exhaust, and it also needs to be at a point where the amount of heat it needs to protect the nozzle from can successfully be insulated by the film cooling of the turbine exhaust gas, as regenerative cooling is often terminated at that point. Some other engines that did film cooling with their turbine exhaust are the engines on the Saturn V. Both of them, actually. The F1 and the J2 utilized turbine exhaust film cooling to keep the lower portions of their nozzles cool. In the case of the J2, it still utilized regen cooling below the manifold, but the F1 stopped doing regen cooling at the manifold because the film cooling was enough to keep the rest of the nozzle from melting. There's a really fun and distinct thing to notice when the F1s were running. Notice the bright orange flame front doesn't actually start at the end of the nozzle. There's this weird dark bit dancing around between the flame and the nozzle exit. That's the turbine exhaust film cooling gas. Because it's so fuel rich, it takes a moment for it to find oxygen to burn with and ignite. This of course doesn't happen until outside the engine, when it eventually will react with oxygen in our atmosphere. But what's confusing is we can see a little bit of this in a closed cycle rocket engine that doesn't have a gas generator and therefore doesn't dump the exhaust gas into the nozzle. I mean, check out the RD-180 on the Atlas V. Notice there's little dark spikes leaving the nozzle. It's kind of similar to the F1. That's from the fuel-rich film cooling and not gas generator exhaust soot. It's not as prominent, but it's still quite noticeable. But you might actually notice some dark spots in some other engines, such as the vacuum-optimized Merlin engine or Rocket Lab's vacuum-optimized Rutherford engine. Rocket Lab founder, CEO, and CTO Peter Beck was talking to me about this in a recent interview.
You know, most engines will run some film cooling, so there's a small amount of film cooling. And in fact, if you look at, you can look at just about any rocket engine on an upper stage, on a refractory metal alloy nozzle like a niobium nozzle, you can see the dark spots. So if you'll notice it's kind of on a nozzle, there's this kind of dark spots that run around the periphery. Well, those are actually the locations of the injectors up in the thrust chamber, and that's where the film cooling injector kind of lies, is in line with one of those dark spots.
But notice the vacuum optimized Merlin and vacuum optimized Rutherford look a little different than the others. When they're running in space, their nozzle extensions glow bright red. What the heck is going on here? That is just the metal getting really hot and then radiating that heat out into space. Well, this is another viable option to keep your rocket engine from melting. Don't forget, there's a difference between radiative heat transfer and conductive or convective heat transfer. Since there's no atmosphere in space, there isn't any air to pick up and conduct or convect the heat. So it's not like you can just run a fan over your engine to keep it cool and expect it to wick heat away. The only option here is to radiate the heat away. Unlike convection or conduction, radiation doesn't need matter to transfer heat, just like how the sun transfers heat through the vacuum of space via radiation. The nozzle extension in the vacuum-optimized Merlin and Rutherford are made out of a very thin metal, usually some alloy, such as niobium alloy or some other material that can withstand high heat loads. Now, the problem with, say, the niobium nozzle extension is it's very thin and relatively fragile. But even more problematic is how reactive niobium is to oxygen. This means engines with niobium can really only operate in a vacuum, and it also means their manufacturing is much more difficult. Another famous engine that used a niobium nozzle extension was the AJ-10 on the Apollo service module. That dark part is niobium. And it's a good thing that engine worked well, because otherwise it could have left Apollo astronauts stranded orbiting the moon. Okay, I think that pretty much does it. I'm sure there's some other fun tricks propulsion engineers employ, but that's really the main ones. And it's really fun to see how engineers choose which systems work best for their engines. But I think to review this topic best, let's just look at the vacuum-optimized Merlin one more time, because it employs almost every type of cooling. At the gas generator, we see both heat sink tactics and a very fuel-rich exhaust employed. This makes sense because the other forms of cooling can't be utilized on spinning turbines. You just have to use high temperature metals and then lower the exhaust temperatures to make sure it doesn't get hotter than those metals can handle. SpaceX uses regenerative cooling for the chamber walls, throat, and the first bit of the nozzle. Then inside the engine, they employ some film cooling with additional fuel in the chamber and near the throat. They also use film cooling from the gas generator exhaust at the nozzle extension when the regenerative cooling channels end. But in addition to the film cooling, the nozzle extension also radiates additional heat away by using a thin but high temperature niobium alloy. The only form of cooling the vacuum optimized Merlin doesn't appear to use is ablative cooling. But considering the upper stages are only used once, this is one engine that could probably get away with a little ablative cooling in a spot if they needed to. I love all these little tricks that engineers have figured out to keep rocket engines from melting. It blows my mind that regen cooling works for some reason, and also that you can use exhaust gas from the turbine to film cool your nozzle too. For some reason, both of those things just seem kind of crazy, and it's amazing that they work so well.
All right, now we'll close here by a bit of a fly through one of the James Webb Space Telescope's first images, what they called the cosmic cliffs in Carina. So this is a region of star formation, so gas and dust in space, about 7,600 light years away in the GUM-31 Nebula, sometimes called the Gabriella Mistral Nebula, and Chris has mentioned that name in the past as well during Astromofo. In the picture, where you see the background stars in the blue and not the dust and the gas, there's actually very, very intense ultraviolet and stellar winds coming from stars that are located above the field of view. So you can't actually see the stars, but what they're doing is they're pushing downwards and slowly eating away at the edge of the nebula. So eventually it would clear it away given enough time. Now this the actual image itself was taken about 6 weeks before it was released publicly, and obviously in that 6 weeks they were working on how to best show it to the public, and it would have been embargoed at that time. Those of you who actually want to see it through a telescope, I show the right ascension and declination at the bottom there. So you just bang that into your telescope and it will point it directly at it. And the image itself is only about 7.5 minutes across. It's about 16 light years so for what you see. So this goes for about 2 minutes. And for the sharp-eyed, you might have noticed two of the names there were two that gave a talk about a year ago, Alyssa Pagan and Joseph Di Pasquale, as about how they process the images from James Webb telescope as well. So they were involved in putting that 3D fly-through. And as you can imagine, given that it's a 2D thing, it would have taken a bit of work to sort of pull out the layers like that to give it the impression that you're flying through the nebula. And with that, we'll close the May meeting, and hopefully we'll see you for the June meeting. Thank you very much.